All right, so we're catching up on recording some videos, and here's class 18. We're going to talk about the Carnot cycle, a very important cycle as the theoretical best cycle that can exist for a given set of heat sinks and heat sources. We'll talk a little bit about the ideal and the real and the comparison of ideal and real machines. So here you go. Here is an image, and we'll talk through the slide a little bit. And so what's the best efficiency that we can get? The best efficiency we can get is to have a completely reversible engine. All right, so we're going to try to create a engine made out of 4 cycles, and each of those cycles is going to be a reversible process. And that is what is called the Carnot cycle. And it's named for a French engineer, Nicolas Leonardo Sayed? Sayed? I don't know how to pronounce it. Said. There you go. Carnot. So he expressed the foundations of this, and which was the foundation for the second law of thermodynamics. So the second law of thermodynamics, which is the chapter that we're dealing with, the Carnot cycle, he's probably the king of this second law. And this was done in like 1824. So if we're looking at the image on the screen here, we start out walking through the cycle. We want to mark it up a little bit so it'll be more interesting. We started with a high temperature reservoir, and we have a low temperature reservoir. Okay, so here's sort of like the premise of this Carnot cycle is that we're going to make an engine or a heat pump refrigerator that goes between these two extremes. These are like a limiting condition for whatever reason. We only have this source and this sink, and we want to use these and find out what the maximum efficiency that we could possibly get, and that's going to be to have reversible processes. So if we're going to go for the engine direction, we're going to start out with isothermal heat transfer, right? So this is the engine portion. We have a boiler, and we're going to take from our hot reservoir, we're going to heat up whatever our medium is. This could be some type of liquid, it could be a gas, it could be a liquid gas mixture, which it often is if it's going to be steam or refrigerant or whatever. That's going to be the main liquid that's going through this cycle. So in this process, we're able to heat up. But it's isothermal, so and which makes it a reversible process. So this begins the first kind of chink in the armor of being able to get a Carnot cycle, because we know that heat transfers from a high temperature to a low temperature. So a isothermal process would have to be one where you did it in very, very, very small increments, but even then you wouldn't be able to do it because you must have a temperature difference for heat to exchange. But here's our first issue for this reversible cycle. Not possible to have an isothermal heat addition from this, but let's just keep on pretending. The next, we're going to have a reversible adiabatic process that lowers the temperature from TH to TL. Right, and in that case, it's going to go through a turbine, right? So we're going in the clockwise direction for the engine in this image, and that's where we're going to extract some work out, right? So we're putting heat in here. I think I'm correct. Yes, we must be extracting work out, so we're able to get the work out of this engine, and then the next process we're going to go. So this was like the 1 to 2 up here. And now, here you could almost call that one 1 and this one 2, I guess you could say, yes. And then we're going to go 2 to 3 through this process, go through the turbine. And of course, that's adiabatic, which means that no heat is involved, no heat transfer, that the adiabatic word means. And so we go through the turbine, we get some work out by way of getting the temperature, dropping it from a high temperature to a low temperature. And then we got to get rid of some heat, this QL. And so we expel some heat down to the low temperature, and that too is an isothermal process. And then, so right here, we're going to get to 4 right up there. And then we go ahead and in this reversible process, we're going to add, we're going to raise the temperature from the low temperature to the high temperature through here. So this would be a pump in an engine to go from 4 to 1, and once again, this is an adiabatic process, right? So what we have is let's see, do the little highlights of the important parts here. In the highlighter, we have reversible, 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 reversible. All right, so this theoretically is the best that we can possibly do. Just to put a little bit more emphasis on this, we could also mention that we could have a Carnot refrigerator instead. And here, where we would go the other direction, right? So you can see that we have, we probably want to start here, because this is the main thing we want to do for a refrigerator, is go from the low, and then you can see these other arrows right here. I believe that's what they are. So we go from this low temperature, and it expands, and then it comes back through here, and we compress it now instead. So we're compressing it through a compressor, or they're calling it a pump here. Compressor, and then it comes through here, which down is the condenser, and then it comes back down through here, which is now, this is going to be like an expansion valve, actually, for a refrigerator type of thing. So just to give you sort of an idea, that we could go in either one of these directions, and in the case of the refrigerator or a heat pump, we need to put work into this. So that's like the big idea behind a Carnot cycle. And here's some other figures that are kind of trying to describe how this might actually be a practical, or I guess in some respect is an impractical type of position. So they're using a plunger in a closed system here, and what we're doing is we're adding heat in an isothermal way. Well, how do we do that? Well, as we're putting heat into this, we are removing these little coins off of this, and we're going to kind of try to heat this and keep it as it's expanding right there, so that we have the temperature remains constant. So we're purposely taking things off while we're putting heat in, and then we and then we keep taking things off when we stop taking heat in, and we allow it to expand, right? So we're actually I believe, if I'm correct here, let's see where I'm kind of drawing with the wrong color now, aren't I? We'll go back to there. We're going to go to the turbine, and we're coming in here, and we are we're lowering the temperature, right? So it's going from this high temperature to this lower temperature, right in here. So we have this adiabatic expansion going on right there, and then we do the isothermal compression. So we're removing heat down to our sink right there. And of course, we're moving these little guys over here, so just in the right amount of way, so this temperature always stays the same. And then we stop that, and then we have a compression right here. We make an adiabatic compression where there's not allowed of any amount of heat, so we can almost kind of show that we're taking the blanket off. We're putting a blanket on right here every time we're doing the adiabatic thing, because we're not allowing heat to come off, but then we're taking the insulation off, and when we're allowing heat to either come in from the sink, from the source, or out to the sink. I don't know if I did a great job of explaining that, but that's sort of the conceptual thing that's taking place in this diagram. And here is the main thing we want to take a look at. So this is a generalized formula for us. We're going to talk in the next video, or I'll just keep continuing this video. No, I guess we'll do it in the next video, where we talk about the thermodynamic temperature scale. But essentially what we're going to say, so here's things to come, is we can make a comparison in this idealized situation, and instead, so we'll write a Carnot efficiency, at least for the engine. So here I'll pre-write what this is going to turn out to be. The Carnot efficiency is, now we can write, it's going to be 1 minus TL over TH. And of course, these are going to be absolute temperatures here, but you can see that we can get this idealized efficiency, the Carnot efficiency, just based on what the temperature of the sink divided by the source right here, and then that right there gets subtracted from 1. And that becomes the maximum amount of efficiency that we can get out of these two temperatures if they are, for instance, this is the temperature that we could get out of the boiler, and this is the temperature that we are dropping it to in the condenser, and we couldn't get any more heat into it from here. and we couldn't, so we couldn't get any higher temperature. This is the limit of the temperature that we could bring the steam to, and this is the limit of the temperature that we could bring the condensate down to. So that's going to be what stops us from getting any better efficiency than what is provided. And we will end the video with that, and then go on to the next section, which is these two propositions, the thermodynamic scale, and then we'll talk about the ideal gas temperature scale, which is probably the one that's going to make the most amount of sense. And then we'll do some examples. So one more video of blah, 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 and then the rest should be, I believe, unless I'm looking at this wrong, yeah, the rest are going to be examples. See you soon.